All right, hello. So I am going to show off this simulation I made. I've been working on it for quite a while, so let's get into it. I have the source code here. This is the main file. I'll compile it quick, and we'll get right into it. So you can see here, visually this is fairly simplistic. It's all black and white. I got a box here with some mysterious particles flying around. I got a little, very simple, very small user interface where I have some sliders. I can adjust some things. Um, But what I want to do in this video is just kind of um, show you, give you kind of an explanation of what this simulation is capable of right now. It's a prototype. It's fairly new, but it can do a lot right now. It can do a lot of things in a very narrow domain, and that's simulating voids on a large scale. Um, so I call these particles, I'll slow this down, these particles referred to as boids. It's short for, I think, bird-like object. It's a computer simulation or type of computer simulation that was made in like the 1980s. So these are just little 2D triangles flying around, and based on these parameters down here, the separation, cohesion, and alignment, they will flock together or they'll just kind of fly around randomly. You have to adjust these to, get your desired behavior. Um, so right now you can see on the screen I have 32,000 of these, but I have this simulation set up so I can go up to millions of them if I want to. Of course, that gets really slow. But before we start that, I'll go over what these parameters are. And to do that, I'll go over to the Wikipedia page. I think this is a pretty good explanation of it. Um, so here, these are triangles just like the ones I have in my simulation. Um, and a Boyd simulation follows just these three rules. You can add some more, maybe random noise in. You can change how the searches happen, but this is like the most basic version of it. So you have separation where each each Boyd or bird-like object just tries to keep its personal space from other birds flying nearby it. Um, and so what this does is like it finds the average position within a certain radius, and it steers away from that average position. And of course, you can adjust the strength at which this happens. Um, so you can think of this as separation, and cohesion, which is similar to that. It searches for the average position, does just the opposite. It tries to fly towards the average position, towards the group, and tries to stay within that group. So I usually the cohesion radius is larger than the separation radius. And then the third one is alignment, and that is where every Boyd tries to fly in the same direction as its neighbors. And this one is, as we'll see later on in this video, this is the most, um, this will show emergent behavior first. This is like the easiest parameter to adjust. Um, the separation cohesion kind of need a balance. Alignment's in a class of its own. So yeah, this is a good Wikipedia page if you're looking to get into it. Um, Getting like a basic simulation, it's relatively simple. You can use some slow algorithms and they'll run fast on modern hardware. This is the 3D version, and there, you can see there's predator boids, and think of those as large birds and then small birds, which are flocking together. Safety in numbers, right? Trying to stay away. And the reason I'm making one of my own is because I think it's cool because you can adjust some of these parameters to get them to flock in different ways, and you get a cool emergent behavior where, a flock on a large scale is more like a fluid almost or a gas. Um, and so we'll see that in a bit as I can describe this better. Yeah, so here we left this going, and these are kind of all stuck in their own little pocket. They can't get past each other. More like I would say a lattice pattern. Turn the size of the triangles up. And the size doesn't change any of the properties. It's just how they're displayed on the screen. So let's try to get at least one cool pattern before I start explaining everything else. something cool to look at. So this is kind of an art form. I'm learning how to adjust these parameters. See, I got something new here. The alignment is very prominent. They're keeping their distance very tightly packed together. All traveling very slow though, so let's increase the speed down here. We'll see some stuff happen. See, look at that. We'll turn cohesion down. Separation is pretty important. It makes the simulation run faster, believe it or not. So let's go. There we are. We got something pretty cool. Let's reset it. You can see there's some some turbulence that forms. Turn the size up so you can see it better. Separation strength. And what the strength does for separation, at least, it causes the birds nearby to kind of push on each other more. So it causes like these, like as you can see, it causes like turbulence or looks like convection or something in a fluid. But yeah, so here I'll turn on the time. So you can see this is just the panel that displays some useful information for me, making the simulation. So I get the Boyd count up here. It's doing about half, or doing almost a million right now, 900,000. Just below that, you can see the frames per second. That's how fast it's being rendered. And not to be confused with updates per second, which is how fast the simulation is happening. That's how long or how many simulation steps happen per second. And the simulation, right now it's a bunch of stages that happen sequentially to sort the birds or the Boids and to update them. So I have all these stages timed out so I can optimize certain parts of it. And then below that, I have the time divided by the number of the time multiplied by threads and divided by the number of Boids. So that's how long each, that's how much CPU time is being used to update a single Boid. Right now, it's less than a microsecond, which is pretty good. Of course, I have my goal down here. I want it to be about 200, maybe 250 nanoseconds per Boid per update, which is definitely attainable, but it needs some optimization from here. But what I have right now, it's a pretty good starting point for doing, cooler stuff in the future. So what can we do? Let's go on like a bit of a scavenger hunt. I'll try to find some different patterns. So let's try to go back to a lattice pattern. So you can see at the start, they're all kind of like almost hexagons if you look really. But here, let's adjust these. So I think alignment's really important. Let's do, see it's different now. You can zoom out. So let's turn the separation down a bit. Maybe the speed down a bit too. So I'm trying to make a lattice pattern, kind of like if you zoom into a material, you see the atoms, kind of aligned to a grid of sorts, but there's maybe some fractures in it where they don't align well. So you can kind of see that now. Maybe I should decrease the speed a bit more. Turn the Boyd size down. So yeah, it's a bit subtle to see. But here you can see kind of like there's a honeycomb pattern if you were to draw lines between these, and then every so often there's a break. Kind of like a metal if you zoomed into it. It's mostly a uniform crystal, but it breaks every so often. And what I can do now is increase the speed, and maybe we'll get these to move around a bit. And if a bunch of them push on each other, they overcome the separation force. And so you get these cool bands forming. It gets very abstract, but you can you usually think of it as terms of a gas. There's enough particles where it behaves like a gas. But if you zoom in, still it's a Boyd simulation. They're flocking birds. But of course, normally you wouldn't see this many in nature. see a million of these things flying around. So here, let's turn this, I'm gonna turn it down to, should we do 300,000? Yeah, there. A bit more manageable. So one thing you'll notice with this, the updates are happening 70 frames a second. Can we make it slower? Just like up the count. See, it's now happening at 2 frames a second. Although I can still pan and zoom, in real time at VSync, and I can change the sliders in real time. This is intentional just so it makes it easier to interact with, because I know I'm gonna get myself into a hang and just um, find a situation that's really slow, and I still want to be able to make changes to this. So the way I have the thread pool set up right now, this runs concurrently across 32 threads. Each stage they wait at a barrier before they move on to the next stage, and I can stop in the middle of a stage before a chunk of work is given to a thread to reset or change parameters. It adds a bit of overhead, but it's very useful for, you know, prototyping this. Um, so let's get a bit more into it. So I showed a lattice pattern. And now this is kind of like a version of the lattice pattern, but I increased the velocity. So now it's kind of, some of the forces are being overcome by all the boids pushing at each other. Let's change it up. Let's go, well, actually, can I decrease the alignment maybe? And increase the separation? I'm decreasing the alignment strength. It's a bit more sandy now. Sure looks like. Let's try going small but strong. That's different. Bit noisier. And I have this button down here. It's called bump. That's because in the version, the way I have the simulation now, a lot of the particles will fall or get stuck on top of each other because they're out of space, and the easiest place to go is right on top of another particle in some cases. So I got this bump, which just adds random velocity to the mix. And you can see when it gets brighter that there's a lot of particles stacked on top of each other. So let's reset this. Let's try to find this cool pattern. It's like popping, like popcorn almost, where the groups, but they're very energetically changing groups every so often. Let's turn the separation down a bit. How do I do this? Alignment, would it be? So here we got the groups. Maybe separation a bit more. So cohesion, we haven't really played with this too much. That's going to keep them in groups, right? They're all going to try to go towards the average position within a certain range. And there's a bit of jitter right now. This might be a bug actually, but it works for now. Strength, really falling onto each other. And we'll keep the separation low, or the separation radius low, but the strength really high. Maybe might have to reset this thing. It's getting a bit slow. Turn the radius up a bit. So you can see how this looks different when you zoom out, because they're in smaller groups now. Well, we turn the strength down at the cohesion. Separation low, radius is small, but the strength is high. Increase some speed. We turn the alignment down a bit. There we go. Oh, speed's a bit too high. Takes a lot of trial and error to get some of these parameters right. And eventually I want to be able to save these. I'll put a box over here so I can just save the whole state of this panel, and then maybe interpolate between them. Like I can just take each one of these sliders and do a linear interpolation um, between like the starting or between one state and the next state. So I could have like this and then go to a lattice pattern. Um, like these globs, they're like amoebas, right? They got like some surface tension to them. That's cool. I haven't seen this before. Turn the alignment down. Bit of a bug in the camera here, but that's fine. Not quite the behavior I want. Separation radius, let's turn the cohesion way down. Alignment strength high. I'll maybe some randomness to it. See, I'm not quite finding it. Oh, this still looks cool. What I want is like these groups here, and I want some of them to pop off randomly. So maybe I need to turn the alignment way up. Let's give it one more shot. So you look for something specific, but then you find something new. It's always cool to play around with. Also one thing that's cool to do is just to you can grab one of these sliders and just like go back and forth. This should be a feature too. Or I can grab a couple of them even. See if I add like a have this happen at a certain frequency, I can make different patterns too. Look at that. Especially when you zoom out, you can see it. It's cool. Couldn't quite find that, but this is cool too. Put the size down. So I have a pen feature where I can just delete some within a certain radius. Or just clear an area. Let's try actually back to the lattice pattern if we can find that again. Separation radius has got to go way up. Maybe turn the alignment down. This behaves like a gas. You can see they're pushing from higher density to lower density. It's not ideal, of course, but turn the count up a bunch. Make it really dense. Turn the cohesion off. This is a pretty good frame rate. We're doing 1200 particles at 40 about. Let's try to get some little balls going again. So we got separation, turn the alignment down. Maybe play with some cohesion more. So here we go, we got them flying in balls like that. Now from here, we turn the alignment up and down. So separation radius, let's turn the strength way up. Oh, and here's where it was. They're kind of swarming in. So one thing I should have done earlier is show you this. So I'll turn the size of the boys way down. I can show you the grid. This is how they're sorted. Um, so instead of checking, I have to search for the Boids based on their position. I'd search the neighborhood of some Boids, and then I can store these Boids in a grid here, and only reference the cells that fall within the range. So this increased the speed dramatically, especially over. I have 65,000 cells here, and the sorting process is actually faster than I thought it would be. Um, but yeah, so it's always a battle between a linear time algorithm and a n squared, or like the number of Boids squared algorithm. So it's somewhere in between right now, closer to a linear time for the searching. Um, but when they're clumped together like this, it's going to be locally, it's going to be an n squared algorithm. So there's room for improvement here. But usually the parameters are a bit different, and see they're farther apart. And I'm increasing the range at which each bird is searching, but the density is lower, so the speed increases a lot. The speed of the simulation. Let's find one more cool thing. I showed some turbulence. Showed some circle. Let's try an iceberg. So we're gonna go back and try to find the lattice pattern. That was a good starting point. Turn the cohesion down. We don't need much of that. So they're all using up as much space as possible, right? And they're really not really dense, but there's a lot of force built up. You can turn the size of these up. So you can see they're in clumps right now. And we can turn the alignment up. And so they get really close. This is, I think, the iceberg. That's what I call it. So we'll turn the alignment radius up and the strength down. So this is between like a lattice, just about. We can turn the alignment up and see the all kind of, it cracks apart almost like an iceberg. Maybe turn the cohesion all the way down. Let's try going down back to a lattice like fluid. And then cracks are forming because they're all very rigidly following their neighbors. So yeah, that's pretty cool. I got a task manager open. Yep. Here is the simulation's running on another tab right now, but this is the thread usage. So I got 32 threads on my CPU, and the utilization is pretty good right now. For extended runs, especially on a laptop, maybe you don't want 100% utilization, but 90 to 100% or 80 to 100% is pretty good for this. And this is wild. It changes based on the parameters too. So the spreading out is pretty good, and it's pretty uniform across all the threads. And the GPU really isn't doing too much. It's more of a CPU bound application right now. Let's actually go back down to decrease the count. Right, so it's running at 800 updates per second. But you can see the CPU usage is down a lot. And then this one stage, which is single threaded, stage of the simulation pipeline, which is single threaded. So that's 70%. The rest are 50%. Actually, can I try to go on the same tab here? Sorry. Yeah, we'll do this side by side, so I can show the CPU usage as I increase the Boid count. It just climbs and plateaus, at a pretty good spot. This is very uniform too. If they're packed together, the performance isn't as good. The utilization isn't as good. Separation down. There we go. They're bunching up like the iceberg patterns. Maybe separation needs to be a bit higher. Give him a bunch of randomness. Make him messy. Then decrease the count, and you see the CPU usage gets smaller and smaller because there's more of the time is used in blocking the threads um, at the individual stages. And so this could be fixed by like using fewer threads as the count decreases. But I'm not at that point yet. I feel like it's more important right now to make this simulate as many as possible. But yeah, we'll turn the speed down and look at these a bit more if I can. Turn the randomness down. Yeah, here we're back where we started. Yeah, that's as far as I go right now. I mean, if anyone really wants to see a more of this, you can look at the GitHub page. I'll link below. Um, but yeah, hopefully you enjoyed me talking for a bit. I mean, I really liked working on this. I think it's very cool, especially to explore all these different, you know, mess with these parameters and see some cool stuff that you wouldn't normally see. Like you're not going to see a million birds in nature, so why not simulate them? But yeah, hope you enjoyed and take care.